Okay, Janet, go ahead and get example 1. And it's on, just use on your handout. Oh, read the words. Turn the page. So your handout has a copy of the book.
I just see comparison shopping.
Yes, go ahead and read that. Yes.
Comparison shopping.
Yes.
Okay. Comparison shopping. You can compare the unit prices of products so you can decide which size to buy. If price is the only factor to consider, the package with the lowest unit price is the best buy. When you are comparison shopping or comparing prices, to find the best value, you should consider factors other than the lowest unit price. For example, if the largest size product is the best buy per unit, consider whether or not you will use it all before it spoils. Some stores have a shelf tag that shows the unit price in cents to change the dollar amount to cents multiplied by 100.
And yes, most stores do have that unit price that gives you the true measurement of things. Now, one thing to consider in this chapter, and I do like the way it described whether it was going to spoil or not, because if you're getting it really cheap but you're not going to use it anyway, right? Mm-hmm. You're just throwing money away anyhow. So what's an example? You go to Costco and buy a 50-gallon drum of peanut butter, but you're single, right? You live in that single life.
It's just like a good deal, but you don't.
Or
You did that on purpose.
Or you go to Walmart. You go to Walmart and buy a regular thing of peanut butter. You're never going to use that. So it doesn't matter how much you're going to save on that, because at the end of the day, you're right. You're single. Your life's a mess. You know, you're not going to benefit from having all that peanut butter. Wow. Okay. Anyway, a perfect example is things that spoil: eggs, milk, and so on. You know, you have the half gallon versus the gallon. If you're not going to use it, it doesn't matter which one's cheaper, right? Bless you.
Thank you.
But when it comes to this example, we're assuming everything's the same, quality and so on. Now I'm going to give you a perfect example. How many in here know what palm olive is?
Palm olive?
Yeah.
Oh yeah.
It's a detergent to wash your dishes, okay? This is something I've noticed. I don't buy off-brands when it comes to that, because Dawn actually creates more suds. It's more soapy. So it's more effective, where palm olive is cheaper, but you're going to use more of the product. So at the end of the day, it actually costs more, even though it's cheaper on the shelf. Does that make sense? And sometimes that happens in life. Or, you know what? Certain things you go and buy, if you like something that much more, then here's a good example. I saw this at Walmart the other day. My daughter likes Rice Krispies, right? I personally don't think there's a difference between Rice Krispies and the generic brand. I don't think that there is.
You mean like the fake brand?
Yes. So I have a cereal thing
Big brand.
that has the lid on it, and I pour the cereal in there, and she always wants that when she comes home. So this Christmas, she goes to pour herself a bowl of cereal, and she goes, "I think this isn't any good anymore. It just tastes different."
Mm-hmm.
She could tell. She could tell the difference.
There's like a little difference in something.
Yeah.
It's not as sweet.
And she won't eat it because of it. So even though the money that I saved, I'm going to be throwing it out and getting the real stuff because she knows.
I have
So
an example.
go.
So, you know the little baby yogurt mouths?
Yes.
Okay, so I
Yeah.
got my baby the store brand, and they were so nasty. So I just got to get some yesterday.
Now, sometimes that doesn't necessarily work. Like, for instance, pasta or rice. Sometimes it's exactly the same. And sometimes the store brand is actually the brand name, and they just repackaged it. That happens. So you kind of figure that out in life. Anyway, when it comes to this example in this section, it's all cost-driven, nothing else. You're not thinking about spoiling. You're not thinking about any of that equation. You're just looking at the numbers of it, okay? So what you did in the last chapter, price is always on top, quantity at the bottom. You divided it, right? Well, what's different in this section is you're going to multiply it by 100. Every time you multiply something by 100, all we're doing is moving the decimal place. So look at this. Aren't these numbers exactly the same?
Yeah. Yes.
So multiplying it by 100, we're getting it over two decimal places. This is what we're focusing on. So this is the only new step in this section, except for when we get the algebra. This algebra one is entertaining. I enjoyed it. So we have 16 ounce, 20 ounce, and 36 ounce. Okay? We divide everything out, multiply it by 100, and this gives us our unit cost. Okay? So which one's cheaper out of these three?
The 36.
Yeah. Now I will tell you, typically this is the case. The larger one is cheaper because larger packaging, shipping, so on and so forth. It's more cost effective, but not always. You know, there's sometimes you could buy 2 units of something that's cheaper than a larger one. You know, and that's why unit price is important, because you can look at that unit price real quick and find what's really cheaper. Okay, so that's first example. Now let's get into this second example. Estelle, can you read that one for me? Example 2.
Like
The
words.
okay. Justin Sanders computed the unit price of 2-liter bottle of a soft drink and found it to be 0.005 more per ounce than the unit price on a 12-pack of 12-ounce cans of the same soft drink. If the 2-liter bottle cost $1.19 less than the cost of the 12-pack of 12-ounce cans, find the cost of a 2-liter bottle and the cost of a 12-pack of 12-ounce cans. Note that 2 liters are equivalent to 67.6 fluid ounces.
Okay, so those of you who had me in algebra, what we're basically doing is this. Can anyone tell me what that is?
Equal to?
Nope.
I forgot.
Means similar in application. Okay? So what's happening is, this problem's a little harder to set up. Now, it gave us enough information. It told us that a 2-liter was 67.6 ounces. I didn't know that. But I do know that a 12-pack at 12-ounce cans, I multiplied, that's 144 ounces, right? So I know that, but so it gave us information that we needed to know. But what it didn't tell us the price. All it told us was, if you take the price of the 2-liter and you add $1.19, that's the cost of it, okay? So we know the price of the 12-pack is $1.19 more than the 2-liter, but we don't know the price of the 2-liter. So we have to use algebra to solve this unknown. Obviously, if we know this, we can plug it in here and solve it for this, right? And it's kind of twofold, because it's telling us it's $1.19 more, but it's also telling us it's 0.005 cents more per ounce. So it's telling us the ounces, and it's telling us the price, okay? So this is how we set it up. Everything to the 2-liter has to belong to this side, and everything to the 12-pack needs to happen on this side, okay? Any questions on how I set this up? What always goes on top?
The variable.
I don't
know.
The cost. The cost always goes on the top. So we don't have the cost of the 2-liter, but we know the ounces, okay? When something is similar in application, it means that the other side has to be the same. Let me explain. Can someone tell me how they put the measurement of a Hot Wheel? Do you guys know what a Hot Wheel is?
A car? A little
Yes.
car?
Yes, little cars. There's a measurement that's on there. Do you guys know what that means?
No, because I don't have it.
Okay, so similar in application is like this.
Isn't it the pressure?
So the Hot Wheel being 1, if you were to take that Hot Wheel and multiply it by 18, you would get the full size. Okay? So this is similar in application. This is saying one Hot Wheel is equal to 18 of those if you expanded it that much. Okay? So what happens with something similar in application, it means they're identical, one's smaller, one's larger. So we have the same situation here, that these equal each other at the end of the day. Okay? That we're comparing these two. Okay, so ounces at the bottom, cost at the top, it's always going to be that way. That will help you set up your problem. Once again, we are going to do 3 and 12 together. So this is how we solve this problem, okay? So having this problem, normally in math, the very first thing we want to do is get things out of fractions, okay? So that means I'm going to take this 67.6 and I'm going to multiply it because it's dividing here, so I'm going to multiply it. That's going to undo it. Then I'm going to do it to the other side, right here. So let's talk about this first step. I want to get rid of the fractions. To get rid of the fractions of division, I'm going to multiply 144 and I'm going to multiply 67.6. Does everyone understand that? Mm-hmm. So by multiplying, I cancel it out and then I do it to the other side, okay? So ultimately what I'm doing is I'm taking this 67.6 and I'm moving it to the side, and I'm taking the 144 and I'm moving it to this side. Now how I do that, it's called an inverse operation, and I'm just doing the opposite of something, okay? So after I do that, this 67.6 is gone. I just combine the 144 and the x together, okay? Then from here, I have distributed property, okay? This is now gone, and I have to multiply everything out. So this 67.6, I have to multiply it by the x, and the 67.6, I have to multiply by the $1.19, right? Because I have distributed property here. This 0.005 cents, remember, I moved this from this side, and I moved this from this side because it was a fraction, so I need to multiply these all out, okay? The hardest part is setting up the problem. The actual math is not hard. From here, we combine like terms. This is an x, right? This right here is a number. I can multiply. These are all numbers. There's no x's. 0.05, so take your calculator and do it. 0.005, 67.6, 144, and tell me what the answer is. Yes, multiply. 0.005 times 67.6 times 144.
28.67.
Okay, so here's this number, right? I combine all these things together, and then I multiply it out of the parentheses. So I multiply this and this, I combine it, this and this, I combined it. Now, can I combine these two numbers right here?
Yeah.
Yeah, so I can add these now. 129.16, I bring down to 67.6. So what I have left is, after I add these, I have this number, the 67.6, and the 144x. So my algebra people, what do I need to do in this problem right here?
Divide.
Not yet, right? I need to get like things on their sides, right? So I have an x, and I have a number. Don't I need to move this x over?
Yes, sir.
Yeah, so I'm going to do the opposite of this. There's no minus in front of here, so I know it's plus. So I'm going to subtract it. Because I subtract this, that's 0, right? That cancels it out. And I go to this side and I do this as well. Now let me explain what we're doing here. I like this example because x and y's, when you get into algebra, it doesn't really tell you what's happening. But I always hear algebra's not used in the real world. It's used all the time. So this is our 12-pack, right? This is our 2-liter. If we subtract the 2-liter, we get the liters left, or the ounces left, that are in the 12-pack, right? That's important because we're dealing with an increase of $1.19 in price and 0.005 in ounces, okay? So that's why it's important. So once we subtract this, we get 76.4. We have this number by itself, and then it's easy to solve from right here, right? We got to get this x by itself, so we're going to divide the 76.4. 76.4, this goes in first. And what we just figured out was the cost of the 2-liter from all this nonsense, from all this information, okay? So our 2-liter is $1.69, okay? But we're not done yet. We also got to figure out the cost of the 12-pack, right? Because the 12-pack is saying it's the cost of the 2-liter plus $1.19. So we have to add those two together, and there's our 12-pack cost. So now we're able to see this. The 2-liter cost $1.69, the 12-pack cost $2.88, okay?
I don't really get the 12-pack for what it is. I mean, it might be $1 more or something, but you get more.
It all depends. It comes down to that use thing again, right? Like, if you don't drink that much soda, as long as you seal that thing up fairly quick, it will keep. Where a can, what happens when you leave a can out and you come back to it, you put it in the fridge the next day?
It's nasty. It's like
All the carbonation's gone. You know, at least in the 2-liter, it can hold it as long as you seal it back up after using it. So that we're not factoring. We're just factoring cost. What is the cheapest at the end of the day? We're trying to compare things. Okay?
Yeah, but with the 2-liter, as soon as you, like, for a long period of time, if the 2-liter goes flat with the cans, it don't matter if you have an opening.
Yeah, they would technically they would keep longer, right? Yeah, because every time you're opening that up, that carbonation is gonna come out. Do you guys know how they do the soda machines at like Circle K and stuff?
No.
So there's a big box of syrup, okay, and that syrup is what the soda is, and there's a combination, a percentage of soda, water versus the syrup, and Coke or Diet Coke, all those have just a little bit different combination, so they have to dial their machine in. So how many times have you ever went in and you're like, this doesn't even taste like Coke? That, it means the percentages are off. It's either has too much soda water, or if it's too sweet, then it has,
Too much.
yeah, too much or too less. And it happens all the time. So, where that combination gets off, or maybe there's something wrong with one of the spouts, it's leaking, or whatever, okay? So, nice thing is, really, this is what you're doing. You can tell this is a little more of a complicated one. You're not gonna have one like this on the test, but tomorrow we're gonna spend time on number 3 and number 12. I'm gonna show you guys how to set those up and how we solve them, okay? Any questions on this? Yes, go.
Why would you put 67 on the word 67.6 next to the 0.005 multiplied again?
Okay, because we have two things going on here, right here, okay? If we got rid of this, we have to multiply it by the x and the 119, but we also have to multiply it by here. So it's like distributive property. So let me kind of give you an algebra example. Let's say we're 3 times x minus 2 plus 3, okay? If this is in parentheses, this means we have to multiply everything that's in here for our problem to be right, okay? Well, we have two sets of the problem. We have this side of the problem, and we have this side of the problem. So that's plus, that's like this being like this. Like if I were to take this entire thing and put it in parentheses, and that's an excellent question. I need to multiply it by this, and I need to multiply it by this as well. Make sense?
Well,
There's two sets of problems. This plus is creating two sets of problems. Just like this minus and this plus is creating two sets of problems. For me to actually get rid of this properly, that means I have to multiply by everything that's in here. So just like distributive property, I can't just do 3x minus 6. I'm not done yet. I have to multiply by this as well. I have to multiply by everything that's there. Okay? So that's why I'm taking this, multiplying by this, and then I have to take this again and multiply it by this because there's two sets of the problem.
can you do the same thing for 144?
Yes. And the reason why the 144 is because it's in the fraction here, and that's division. Multiplication is the inverse operation, so that's why we're doing it on this side, and that's why we did it on this side as well. Okay? So we multiplied it to get rid of it, and then we had to do it to the other side. Okay?
Gotcha.
Okay, any other questions?
No.
Are we good?
Yes. It's
You're-
easy.
Okay, you're welcome.
Thank you.
Don't forget to multiply 100, that's the only thing that's different, and then compare, and then most of your answers, you're saying what is the cheapest? It's just cost, whichever one is the lowest number.
Okay, so we're dividing first, and then multiplying, and then.
Yeah, and wasn't this 6.3?
Yes, sir.
The only thing that's different is taking the number and multiplying it by 100. Okay?
Yeah.
Okay, now remember, two decimal places now, where before you were 3, now it's 2 when it's all said and done.
Okay.
Okay? All right.